Okay, this is 14.4, video 2. So in the last one, we were talking about linear approximations at the end and linearization. So we're going to talk about differentials, which kind of goes with linear approximations and linearization. So let's do a remember or recall in 2 dimensions. If we were doing a differential, the general idea was if you had a curve and we had some point on the curve that was known, we could draw a tangent line to that curve. And what we could do is we could approximate a value which is relatively close. Now, it's not going to look like it on my graph here, but we're going to say that this is a relatively close point. That would be the actual value on the curve. This is, right here, this distance from basically right there to right there, that would actually be the actual change of y. The differential, however, is the distance from here up to right there. I think I made my bracket a little bit too big. So it's the change in y on the tangent line as opposed to the actual change in y on the curve. That's what's called the differential. And the way we found the differential was, because as you can see, the differential is dy. We have to realize that dy over dx is the same thing as f prime of x. Well, then to solve for dy, you simply multiply dx on both sides, and what we would get was that dy equals f prime of x dx. So that's what the differential of y is. So in 3 dimensions, it's relatively the same idea. We're going to start off with the fact that we know that we can write the derivative. It's going to be slightly different in this case. We're actually going to start off with the fact that we know the tangent or linear approximation of a tangent plane can be written like this. Now that fx and fy would normally be evaluated at a point, but in general, that's what it would look like. So what we have to realize is, well, okay, what is z minus z naught? That's just the change of z. That's dz. Okay, fx is the partial derivative with respect to x. X minus x naught is the actual change in x. That's dx. Okay, fy is the partial derivative with respect to y, and then y minus y naught is dy. And there's your differential equation. This is the equation that you will use to find differentials in 3 dimensions. All right, so let's go ahead and do an example. Let's find the differential of the function z equals x cubed ln of y squared. So, according to this, what we need is we need the partials. So let's do partial with respect to x. Well, that's going to be 3x squared ln of y squared. And we'll do the partial with respect to y, which is going to be, it's going to be a bit of a chain rule here. So x cubed just stays as a coefficient. And then let's see, it's going to be 1 over y squared times 2y. And that's going to simplify. The 2y goes on top of the y squared, so it's going to simplify to x cubed times 2 over y, so 2x cubed over y. So then dz is fx 3x squared ln of y squared dx plus fy, which is 2x cubed over y dy. And that's it. Now keep in mind, dz and delta z are the same thing. They are the change of this. I'm sorry, they're not the same thing. dz is the approximated change of the z values based upon the tangent plane. So it's what's actually happening from the curve, from the known point on the curve up to the tangent plane, where delta z is the actual change in z values, or in this case of your f of xy values. So dz is an approximated, delta z is an actual, but again, the closer and closer and closer we can make delta z and dz, the closer the approximation is going to be. All right, so let's take a look at one where we actually have some numbers to deal with here. Come on, there we go. So if z is 5x squared plus y squared, and xy changes from 1, 2 to 1.05, 2.1, compare the values of delta, I should actually say delta z and dz. All right, so let's find both of them. Let's find delta z. That's the actual change. So delta z is going to be f of 1.05, 2.1 minus f of 1, 2. Of course, I don't expect you to do this without a calculator, so you're going to plug 1.05 and 2.1 into your original function, and that works out to be 9.9225, I think, if I got that. Yeah, 9.9225. Plugging 1 and 2 in, we can actually do without a calculator, but you can do it with a calculator as well. You're just going to get 9. So if you subtract those, you just get 0.9225. That's the actual change in z. Now let's find the differential, which is dz. So in order to find the differential, we need the derivative with respect to x, so that's going to be 10x dx, plus the derivative with respect to y is 2y dy, and then we're going to plug those values in. So dz is going to be, let's see, 10 times the known x value is 1, so 10 times 1 times the change of x, which is 0.05, because it goes from 1 to 1.05, so the change is 0.05, plus 2 times the y value is 2, times the difference, times dy there, which is going to go from 2 to 2.1, so that's 0.1. So we're going to get 10 times 1, which is 10, times 0.05, which is going to be 0.5, plus 2 times 2 is 4, times 1 is 0.4, so 0.5 plus 0.4 is 0.9. It's a pretty close approximation. It's certainly not exact, and we could do much better, but that's not that bad of an approximation. Okay, let's look at number 7. It says the length and the width of a rectangle are measured in as 30 centimeters and 24 centimeters respectively, with an error in measurement of at most 0.1 centimeters in each. Use differentials to estimate the maximum error in the calculated area of the rectangle. Okay, so the first thing we need is the area of a rectangle, which is just length times width. Okay, so if we're going to call the area basically like our z, in this case, I could have called it a. It doesn't really make any difference. I'll just stay with a. Just keep it better that way. So we're going to have dA, which is the differential. Now this is going to be a product rule. It's going to be dA dL, the derivative of this thing. Oops, that should be a partial. Derivative of A with respect to L make it a capital L like it is up there, times dl, plus the derivative of a with respect to w times dw. And if I said product rule, I apologize. It's not a product rule at all. It's just the differential formula. But we have the information that we need. So dA here is going to be, let's see, dA dl, it's the partial with respect to L, and the partial of this equation with respect to L is just W times dl, plus the partial of our area equation with respect to W is just L times dW. So it kind of does look like a product rule if we go back to implicit derivatives. But now we can plug this stuff in. So we get that dA, W was measured to be 24, according to our information above. dl is 0.1, plus the length was measured to be 30, and dw was also 0.1. So we're going to get 2.4 plus 3, which is 5.4 centimeters squared, because we're talking about area change. So that's the maximum error of the calculated area of the rectangle, 5.4 centimeters squared. Okay, should only have one more, I believe, on the next page. Yes, one more to go. Use differentials to estimate the amount of tin in a closed tin can with diameter 8 centimeters and height of 12 centimeters if the tin is 0.04 centimeters thick. Okay, so you got to think about the drawing of this. See if I can do any justice. So you're going to have your can, which looks something like that, but then it also has a thickness to it, and this is where my lack of skills is going to show up. It's got some kind of a thickness to it, so I'm going to have a... Okay, that wasn't horrible, but it wasn't great. There's going to be a thickness to the inside of the can. So basically, if you think about it, even though it's really thin, there is a thickness to it. So the top piece up here is 0.04 centimeters thick. We know that the height of the can is 12, and the diameter of the can is 8. I also know the equation for the volume. Volume of a cylinder is pi r squared h. So if we are going to find dV, remember that dV is going to be the partial of V with respect to R dr plus the partial of V with respect to H dH. So let's find dV. So the partial of V with respect to R is going to be 2 pi r h dr. Plus, then we're going to get the derivative of the volume with respect to H, which is just going to be pi r squared dH. Okay, and this next part's the hard part because, again, this comes into the fact that I have a really difficult time with the drawing part of this. And if you can imagine this, great. If not, I don't know how else to explain it. So let's just write what we know. We know that's 2 pi. We know the radius is going to be 4. We know the height is 12. Now the dr part, that one's not that bad of a thing. The dr part is right here. All right, because that's the change in your radius. That's 0.04. And then we know we've got pi times, again, the radius, which is 4 squared. It's the dH part that's a little bit more challenging. If you can picture this. Now, again, I said that there is that that thickness to the can. There's usually a lip out here. I don't know how to draw this, but it's kind of like a rounded lip that kind of goes around, I guess, this thing right here. That's part of the thickness of the can. Well, there's going to be one of those rounded lips on both the top and the bottom of this thing. Again, I don't know how to draw this, and this is horrible that I can't figure this out, and I still haven't figured out how to draw that. But there's kind of that, like that rounded lip or whatever at the end. So there's a difference in the thickness here of not only 0.4, because now it's this direction, but it's 0.4 twice. So it's going to be a thickness of 0.08. I keep saying 0.4, it's 0.04. Then it's 0.08, which is twice the thickness in the vertical direction. Again, I have no idea how to draw that better. I wish I could. But that's what you're looking at. And then, obviously, you'll plug all this stuff in. I'll have to pause it here for a second because I didn't plug all this stuff in yet. All right, so it looks like we get, we get that dV here is going to be 3.84 pi plus 1.28 pi. So we're going to end up with 5.12 pi. And then obviously you could get an approximation if you plug in pi. But that is going to be your differential in the volume. And this would be, let's see, centimeters cubed because it is a volume. All right. So there's your lesson for differentials. That should be plenty enough.